So one good thing about Jamovi is that it gives the uh, graphical output of high resolution. And this graphical output of high resolution is much desired by the academic journals. So the basic descriptive statistics is that we calculate is the mean, median, mode, standard deviation, skewness, kurtosis. So here we have a data. I'll show you where you will get this data. So let me get with this. So this is the data that I'm using as the sample data which is built in Jamovi itself. So if you have to open the data which is built in Jamovi, you need not to import or something. Simply click on open and go to data library. Here you will find four kind of data sets. There are many others, but basically these four are able to explain most of the statistical test. So I am taking this data set known as bugs. So this data set is having this subject means respondents. This is a dummy variable, respondent serial number, their gender, male or female, their region, to which part of America, Australia, or which part of the world they belong to, their education level. Then this is a score out of 10 about their willingness to kill a bug or kill these insects or the bugs based on their disgustiness and frightiness. Means how much they are frightening and how much they are disgusting. Based on that, this is the willingness of the people on a scale of 10 to kill those bugs. So LDLF means low disgustiness, low frightiness. LDHF means low disgustiness, high frightiness. Then HDLF means high disgustingness and low frightiness, and HDHF means high disgustingness and high frightiness. So actually, if you want to calculate, so for the gender we can calculate only frequency. There is no point in doing any mean, median, mode. But for these variables, since these are continuous variables, we can calculate mean, median, mode also, and also visualize them. So let's first do the frequency distribution for these genders, how many of them are male and how many of them are females. So exploration, descriptives, and from here you can take gender. That's it. In statistics, what you want, sample size, yes. If there is missing value, then that also. Mean, median, mode we don't want because it's a categorical data. This standard deviation, minimum, maximum, nothing, only frequency distribution. So if you see, we have total 92 and there is one missing. You can see that which one of them is missing, or you can leave it, or yesterday I told you how to replace the missing value. You can report it and do that. Now, if you want a frequency table, click on this frequency table and it will tell you how many male and females are there in your sample and what is their population. Side by side, you can calculate this also. Now let's calculate the scores. So these are the scores. Now if you want to split it by gender, means this is the total numbers and here we want the mean also. So this is the mean value on a scale of 10 we have taken. So this is the mean value If you want to split it by gender, then you can split it by gender also, and see in each case that how many males and females, what is the mean score of male and what is the mean score of females regarding their intention to kill a bug based on the LDLF, LDHF, SDLF or SDHF scores. Now, here if you want to plot something, if you want a plot, you can create a plot also side by side. So if you want median values, you can select median values also in the same table. If you want mode, you can calculate the mode also. So all these mean, median, mode you can calculate. Now I simply want in the next step the visualization. So I'm removing all the statistics. And the moment you remove this, the entire this will become blank. Whatever test you want, only that will appear. So if I want to visualize it, first thing that I want to visualize is the histograms. Histogram for each individual item. How this data is distributed. Here's, yeah, I have split it by gender. I'm removing this. Now, you see. So this is the distribution. Now, if you want to check that whether this distribution is normal or not, then you can do one more thing through visualization itself. You can plot a density plot over this. So on all this code, a density plot will be plotted. So you can see from the density plot that this one is somewhat normal, but other one are highly skewed. And why? Let's see the box plot of it. Click on the box plot. So for individual, it is giving the box plot. Now, box plot is a plot which is very useful for exploratory data analysis or for initial view at the data, because it tells you about the minimum bound, the lower bound, the upper bound, the median values. It is also used to compare uh, two data sets side by side, and it also tells you about normality. How it tells you about normality, and also it tells you about outliers. So for normality, this median value, this is known as the median value. It should be exactly at the middle of the plot. This is known as, this box plot is also known as box and whisker plots. So this is the box and these are the whiskers. So this is the lower whisker, also known as quartile 1, and this is the upper whisker, also known as quartile 3. So the length of the upper whiskers and the lower whiskers should be same. There should not be any outlier, and this one, this median should be exactly at the middle of the box. So here you can see that it is somewhat far from the middle of the box. And if you see the whisker, the lower whisker is greater than the upper whisker. Slight difference is there, and if you see, that's why the data is somewhat normally distributed, not completely normally distributed. But if you compare with this one, highly skewed, and see its box plot, it is having outlier also, one outlier, and outlier actually is represented by this dot, and lower whisker is far greater than the upper whisker. Let's see the third case. Third case also the thing is the same. And fourth case, highly skewed. If you can see, only you have a lower whisker, no upper whisker here. So this box plot tells you about the normality, about this the lower value and the above upper value, and it also tells you about outliers. So In one of the case, we also found one outlier also. Here it is a, there is one outlier in this case, LDH. Now, another plot is known as which you want to create only density plot. So density plot is just the line diagram representing the distribution of histogram. Without histogram, if you draw, it will be like this, as we have found it earlier also. So this is the density plot that you can find. Then if you are plotting a box plot, it's also a better idea to plot a violin plot. Violin plot tells you about how the data is distributed. So if you draw this violin plot over this, so it will tell you that across this box how the data is spread, and if you want to have a better look, just click on this data. And it will tell you that how this data is spread in across this box and this curve plot. So this is one, this is another shape. So these are the violin plots. If you only want violin plots, remove the box plot. You will only find violin plots here. These are the violin plots showing the data. And if you remove the this will tell you about only just violin plots. Now there is another plot that you can draw, that is the QQ plots, quantile plots. This plot also tells you about normality. So across the diagonal line, they actually tells you about the normality of residual errors. So anything that does not lies on the any data point that does not lies on this diagonal line is known as a residual error. So whatever lies, this will be helpful for you in regression. Whatever lies above this line is the positive residual, and whatever lies below this line is the negative residual. If data points maximum lies on this line, then we say that there is a normality of residual errors. So in first case also, you can see there is no normality of residual errors. Here, highly scattered, again there is no normality. Here also there is highly scattered, and here also they are highly scattered. So there is no normality of residual errors. Then you can also draw a bar plot if you just want to have a frequency distribution of them. So this is one bar plot you can see. Now coming to the histogram that we have drawn, you can divide this histogram as per the gender also. Let's say. Now it will give you a distribution of, it will split the entire bar histogram into males and females. How males that are data, that willingness of the males and females are distributed. Where it will be useful when you will be conducting independent sample t-test. Then this histogram will be further useful for you to represent if you are finding any significant difference between the two groups, then it will help you to visualize that through graph also, that whether there is a significant difference between the two groups or not. So you can do like this. So these are the basic graph that you can draw. Another graph is scatter plot, which tells you about correlations. So for that, I'll take another data. So open, and I'll take this data, this big five. It is a continuous data containing five variables on neuroticism, extraversion, openness, agreeableness, and conscientiousness of the people, psychology of the people. Five psychological parameters have been measured. And let's say we want to see the correlation between neuroticism and extraversion. What is the correlation? So that you can check through correlation, but initially if you want to see the relationship between them through visualization, then you can draw a scatter plot. So if you draw here, there is a, if you click on exploration, you will get an option of scatter plot. And let's say neuroticism and extraversion we have taken. Now you have got this scatter plot, but it is not making any sense unless you draw a straight line to it. So put it on a linear equation. Now, if you can you tell me from this what you can infer? What is the relationship between extraversion and neuroticism? Through this graph, can you tell me any relationship between the neuroticism and extraversion? Isn't it that as neuroticism increases, extraversion decreases?
Yes, sir. -1.
So there is a negative correlation. How much that correlation coefficient, that we can calculate through correlation. But initially we can tell that this is the relationship. We can visualize it. If you want, see, this is the mean value. This is straight line. If you want to plot the standard error also on this mean value, just select the standard error. And now standard error will also be visualized. That across the mean value, what is the standard error, which you will report in descriptives, but you can also you can also visualize it through this graph. So these are the basic, and if you want to, let's say, I want to check this correlation, or I want to check between openness. So this shows there is no correlation, right? This is straight line shows there is no correlation between neuroticism and openness. Now let's remove any other variable and yes, agreeableness and openness. So it is showing that there is a positive correlation. Now, if you want to save this file, simply you can either copy it or export it as a PNG file, which is the high resolution file, or EPS file. Most of the journals like Elsevier and all ask you to submit your uh, diagrams or the images that you have created using statistical software in EPS format. So you can take either PNG or EPS format that you can, and this will be a very high resolution. So very clear. So if let's say if I take it as a PNG, if I export it as a PNG and export the folder on which I was working, it has gone there. Not in this one. I think another folder. Let me see what is my working folder. 9 to 12 March 2022. Yeah. So it has gone into this folder. This one I have saved. You can see this is a very high resolution image which I can use in my research paper. So actually, as compared to SPSS and Excel, R and Python both give the image of very high quality. And since this software works on the background of R only, so the resolution is very high. So you can use this graph to create density plots, to create box plots, to create this scatter plot or histogram. So all these things you can do. Now, let's move on to the. So this is about the descriptive statistics that you can use mean, median, mode. You can calculate standard deviation, skewness, kurtosis, all at once. Here you can have your data and you can select descriptives and whatever you want. Let's say if you want this, it's mean, median, all these things. If you want to calculate mode value, we can calculate mode, skewness also, kurtosis also. This you can see. So all these things you can see, and if you want to check its normality, also you can check. So data is not normal. Already we have seen through density plots also. And if you want to plot it, let's say histogram with a density plot. So you can see that there is a little bit of skewness in this. So like this, you can create the charts, diagrams, or you can create it, or you can make descriptive statistics, and then you can go for checking the normality, or visualizing the mean, median, mode, or dividing it by group also. These charts, as I have told you, like if I want to split it by, however, we don't have any categorical variables, so I cannot split it, but let's take example of the another data. If you want to create some chart by splitting it, like this one we had from data library. Let's take this iris data. So this data set was developed by Anderson way back in 1929, and still it is very relevant. It contains a data of uh, around 150 flowers, which are divided into three species: Setosa, and then versicolor and virginica. These are the three varieties of the iris flower, three species of the iris flower. And he has measured their sepal length, sepal width, petal length, and petal width. So let's say if you want to create a descriptive statistics of, because this is the continuous data, so you can calculate the mean, median, mode. So if you want to do it, simply you can go to exploration, descriptives, and let's take all at once: sepal length, sepal width, petal length, and petal width of the flower. And you can have the, from here you can have the mean value, and if you want to draw if you want to make a frequency table, you can make a frequency table. Now if you want to split it by species, we have three species. Now again you will get the species wise data, that what is the mean petal length of Setosa, what is the mean petal length of, but because previously when we have not taken, it was giving you the mean petal length, mean sepal length, mean petal width, and mean sepal width of all 150 flowers. Let's say you want to have the data or divide this data as per the species, that a particular species, how, what is the sepal length, sepal width, petal length, and petal width. Then you can split it by species. Now here you can get the sepal length, mean sepal length of the Setosa, versicolor, virginica, then sepal width of these, then standard deviation, minimum, minimum, all. And if you want to visualize it, then you can visualize it either with the help of histogram or density plot. Now it will give you species wise their distributions. So the same thing that you are getting, you can get through this. And if you want to make their box plot to check whether they differ or not, so box plotting also helps you to compare. Now you can see that Setosa, versicolor, and virginica, all three differs in their sepal length. However, in virginica you have one outlier also. There are many outliers. So in sepal width also they differ from each other, and in petal length also these three species differ from each other, and in petal width also these species differ from each other. However, if we remove this group wise comparison, then only we will get the box plot of the sepal length, sepal width, petal length, and petal width. We can identify whether the data is normally distributed or not. So data is not normally distributed, because I already told you that for uh, data to be normally distributed, which you want to represent by box plot, this median value should be exactly at the middle, and the upper whiskers and the lower whiskers should have equal length. Or if you want to see it more, you can plot a density curve and you can see. So for sepal length, again, somewhat skewness is there. This one is somewhat normally distributed sepal width. You can see from here due to this, and there are some outliers also. This is highly skewed. This is also highly skewed. So this box plot tells you about this also, and you can divide. And suppose if you want side by side comparison, then simply split it. Now you will get the whether there is a significant difference through this diagram or not. So this you can do. Now let's move on to the comparison of means. Whatever we have visualized, let's do it in numeric form through t-test, which is again three types: independent t-test, pair t-test, and one sample t-test, and also through Anova. So we'll be taking this data for Anova, will be taking later on. So I'm taking on a new data, and let me open my file of PPT. So whatever we have visualized, that was just comparison of means, because our data was continuous data. Now, apart from visualization, if you visualization has told us that there is a significant difference, there is a difference, but whether it is significant or not, that only we can know through t-test or ANOVA. So when you have only one variable, right? There is no dependent variable, there is no independent variable, only one variable, and you want to check that whether this variable, the data that you are getting in the sample, whether it is the true representative of the population or not, or whether you want to test that the sample mean is equal to population mean, or there exists some significant difference. So, and you have only one variable. So this is of one sample t-test. So the hypothesis, the data requirements for one sample t-test. First, try to understand that you have only one variable and you want to check that whether that variable is the true the data taken on that variable, because you are taking the data from the sample, it is the true representative of the population or not, or the mean value of your sample is as same as the mean value of the population or it is different. So before moving on, this makes it a case of one sample t-test. But before moving on to one sample t-test, there are some data requirements that needs to be met. First one is that the variable that you are going to test should be taken on a continuous scale. That is either interval or ratio. And scores on the test variable should be independent. The variable that we are going to test is known as the test variable. That should be independent. It means every score, let's say you have taken 100 samples, every score should be independent of each other. It should not be the case that you have taken 10 observations and rest 90 observations you have said that based on these 10 observations, other observations will be like this only. You cannot do that. Let's say you entered into a class, you want to understand whether the students studying in a undergraduate course, let's say many of the studies suggest that the average age of students studying in the first year of UG course is 18 years. So you have taken a few observations, let's say out of 100 students, only 10 observations, you got 18 to 19, 18 or 19 or 17 like this, and then you assume that the rest 90 will be like this. That should not be the case. Each and every observation should be independent, taken independently. Data should be taken randomly from the population, then only it will follow a normal distribution, the chances will be, and every representative of the population will be in the sample, the chances will increase. Data should be normally distributed, and there should be homogeneity of variances, no outliers. And the hypothesis that we make is null hypothesis says that mu is equal to x bar, that is the sample mean is equal to the proposed population mean, where mu is the population mean and x bar is the sample mean. If you are saying that the sample mean and population mean are equal, that means there exists no significant difference. So normally when you write there exists no significant difference, you are trying to say that both the mean values that you are trying to test is same. And alternate says that mu is not equal to x bar, means both the means, that is the population and sample mean, are not equal. That means there is some significant difference between them. So this is the case of two-tailed hypothesis. There are two kinds of hypothesis, one-tailed and two-tailed. When you are very sure that a situation will occur, then you can frame one-tailed hypothesis. That is, rather than framing a null and alternate, you frame only one hypothesis, that mu is greater than x bar. Let's say you are sure, or mu is less than x bar, right? Otherwise, if you are not sure, and this surety will come from literature review. If many of the literatures are suggesting the same thing, okay, then you will frame only one, and you are sure that this is going to happen. Let's say many of the literatures have suggested that people who do rash driving, or people who drive at a speed of more than who drive at a speed of more than 100 kilometers per hour are more prone to accident. If this is established by many studies, then you can frame a hypothesis, a directional hypothesis, that people who drive at a high speed are prone to accidents, and you will check the same thing in your sample. However, if you are not sure, because another situation could be that people who drive at a fast speed might reach earlier to their destination. This might be a case also. If some literature supports or you are not sure, then you make a null hypothesis and alternate, that is a two-tailed hypothesis. First hypothesis will be the null hypothesis that they might meet an accident. Alternate could be that they might reach early. Or you can say there exists a significant difference or there exists no significant difference. So null hypothesis and alternate hypothesis are bidirectional or two-tailed hypothesis. Whereas when you might have seen many people framing only one hypothesis rather than null and alternate, that is known as directional hypothesis or one-tailed hypothesis. Either this will happen or this will not happen. They are sure about it. And that surety comes from the literature. So most of the times when you are doing one-tailed hypothesis, might be that you end up in doing some error, type 1 or type 2 error. I'll come to type 1 and type 2 error. So to minimize that, it's always a better idea, particularly if you want to minimize type 2 error, it's always a better idea that you frame both the null and the alternate and test the null against the alternate when you are not sure. For minimizing type 1 error, increase the confidence interval. If you have taken 95%, try to increase it to 97%, 98% means margin of error should be decreased. What is type 1 error and type 2 error? Simply, it is what you have predicted, that is truth, that will fall into the first quadrant, that is known as true positive. What you have predicted, that is false, that is not the actual thing, that is type 1 error. Means you have rejected a null hypothesis that stands true in the population, right? Falsely you have rejected. Then what you have predicted to be true is not correct. Okay, so this is the false negative, right? So what you failed to predict, actually you have predicted something that this will not happen, but actually that will happen in the population, that is the truth, that is known as the type 2 error or false negative. And then what you were unable to predict and that is not happening also, that is known as the true negative. So whenever we do a hypothesis test, we always divide our entire frequency into this quadrant, and the accuracy of our test is the total number of true positives and true negatives, while the failure in our test is total number of false positive and false negative. Here, false positive is the type 1 error and false negative is the type 2 error. Always try to not to commit these errors. So when you are making one tailed hypothesis without being much sure, chances are that you will end up in doing type 1 or type 2 error because you are biased. Your result might be biased. So it's always a better idea to make null and alternate hypothesis. You give equal opportunity to for testing both the hypotheses to check on that whether you do not do any of this type 1 or type 2 error. So one example of type 1 error could be that somebody who has been suffering from having all the symptoms of COVID-19, okay, have suppose somebody having not having any symptom of COVID-19 has been tested positive for COVID-19, or somebody who is not diabetic has been tested positive for diabetes. This is something which is not true, but you have actually predicted it. So this is the false positive. False negative is the case that you have failed to predict, which is actually true. So somebody having diabetes or somebody having all symptoms of COVID, but through the test you fail to detect that he or she is having COVID-19 or diabetes, right? So this is the case of false positive and false negative. The total number of false positives and false negative in a statistical test, these are the errors. The actualities are total number of true positive and true negatives. To avoid this, always try to make two-tailed hypothesis rather than one-tailed hypothesis. Is this clear?
Yes, sir.
Okay. It's always a better idea to make two hypotheses, two-tailed, and check whether which one is the, unless you are very much sure. If you are almost sure to a level of 99%, then only you should frame one-tailed hypothesis. Or if you are doing some structural equation modeling where you cannot frame two hypotheses at once, so directional hypothesis, either a positive effect or a negative effect will happen. That kind of thing you can do. Now let's do this one sample t-test in our data. So let's say I am taking only one variable, sepal length, because here you should have only one variable. And a few studies have suggested that normally an iris flower have a sepal length of 5 inches. In a population, if you take all iris flowers, they will have a sepal length of 5 inches. Now, we want to test that from our 150 samples that we have taken, whether the mean length of sepal length is 5 inches or it is different from that. So we can frame our hypothesis like this. Are you getting the problem statement?
Yes, sir.
So this hypothesis could be that mu, since here I cannot write that mu symbol, mu is equal to x, means there is no significant difference between the population mean and sample mean length of the people of iris. Our alternate hypothesis will be mu not equal to that is there is a significant difference where the value of mu is equal to 5 inches. We can write this hypothesis like this also. H naught mu H naught could be mu is equal to 5. Sorry, x bar. This is so we can write x bar is equal to 5 is equal to mu, and alternately we can write x bar not equal to 5 inches, right? Or if we want to, if we are very sure we want to make one tailed hypothesis, then we can write like this. Only H hypothesis that x is greater than 5. If we are sure that in our sample we will be getting, if we are very sure that whatever the study has been done in the population that cannot hold true, my initial observation and all things have suggested that normally iris flower has a sepal length more than 5 inches, or you can write it like this also. If you are sure that it is less, then you can write like this. This is an example of one-tailed, and this is an example of two-tailed hypothesis. Is this clear?
Yes, sir.
Now let's test this in our sample of 150 flowers. So you have to go to t-test and select on one sample t-test. Now this is the sepal length which we are taking. What will be the test value? What will be the test value?
5.
5. Now here all three forms of hypothesis are given. Not equal to test value, null hypothesis, or greater than test value or less than this test value. That already I have told you. Now see what you are getting. P is less than 0.05. Correct? Here can you see the P value? It is less than 0.05, right? So null hypothesis is rejected or accepted? May I have response from you people? Will we reject the null hypothesis or accept the null hypothesis? Am I audible? So the thumb rule says that if P is less than 0.05 or P is less than your significance value, which is also known as alpha, reject null hypothesis. So if you are rejecting null hypothesis means you are saying that there, if you are rejecting this, you are accepting this one, that there exists significant difference between this sample length and the population sample length of iris flower. What is that difference? This one sample t test will give you the significant difference that, but how much difference is there, that you will come to know only by the mean values. So simply take sepal length and calculate its mean. So what is the mean value, mean length that we got from our sample? Am I audible?
Yes, sir, you are.
So this is 5.84, correct? In our sample, we got the mean value of the sepal length 5.84. So this p value suggests that there exists no significant difference, means mu x bar is not equal to mu. And this is also obvious in our mean, so we can report like this. P at the degree of freedom 149 is equal to 12.5. P is less than 0.05. So null hypothesis is rejected, which states that there exists a significant difference between the mean sepal length of the sample and that of the population. To make it more clear, you can write mean sepal length of the population, which is the assumed mean actually of the population, was found to be 5 inches, whereas mean sepal length in the sample was to be 5.8 inches. So you can write like there is no significant difference. That also you can write, or you can also write x bar is greater than 5. This hypothesis also you can write. And then further you can report this difference varies from, you have to see this minimum and maximum value. 4.30 inches to 7.90 inches at 95% confidence interval. That is the total interpretation of this output. Is this clear?
Yes, sir.
Fine. Now, second case is similarly you can do for the petal length, petal width, and all. You can select all these and you can get whether they are differing or not. You can assume and see. You'll get all these mean values, and you can assume and see whether your assumption is different from this, or equal to this, or greater or smaller. You can put your hypothesis and test. This is the case of one sample t-test. Now, second situation is that now you have a dependent variable and an independent variable. In this case, we were not having any dependent or independent variable. We were having only test variable, and we wanted to test that whether it is equal to the mean, it is equal to the mean value of the population or not. Means if it is equal, then it is the true representative of the population, or it is drawn from the same population. If it is different, then it will differ. Now, one more thing that is you can calculate, and that here it is given. So this one we got, that is the, where it has gone, effect size. So okay, so this is descriptive. In one sample t-test, sample length, test value 5 we have taken. So this was what we got. Now we are saying that there exists no significant difference. Means the means are not the same. But what is the effect? Because we have only 150 samples. To what level we can generalize it in the population? So that will be told by effect size. Normally we calculate this effect size manually by using Cohen's d formula. But here this software gives you a unique feature to test the effect size also. So at 95% confidence interval, the effect size will be 1.02, which is very less. So normally the result that you are, so see, it has calculated the Cohen's d. So when you are trying, since this Cohen's d is very means less, having less value, so based on these 150 samples, you should not try to generalize the entire result of the entire population. You should not say that all iris flowers will be having a sepal length of 5.8. You cannot generalize because this effect size is very less. Effect size tells you that the result that you have got from your sample, and the range at 95% confidence interval is this much only. So this effect size tells you that the value that you have got from your sample, how much it is applicable to the entire population. So if it is a very low effect size, means the result that you have got have a very low significance in the population. So based on only 150 samples, you cannot generalize to the entire population that all iris flowers will be having a sepal length of 5.8 inches. That is that you can infer from the effect size. Is that clear?
Yes, sir.
Fine. Today I'll cover only independent and Prt test, and then Anova we can do. So now I will again move on to the independent t-test. Now what is independent t-test, as you all might be knowing? This is the case of one sample t-test. When you have one dependent variable and one independent variable, where independent variable is categorical, and that too, the categories are given are coming from two different populations which are mutually exclusive of each other. Means both categories are different. Like I want to test the exam performance of the students, where students are divided into male and females. I want to check the scores of males and females separately and want to compare that in the exam who performed well, or whether there is a significant difference between the exam scores of male and females or not. Because males and females both are mutually exclusive of each other. Or I want to perform the same test on students having higher attendance in the class and lower attendance in the class. Again, their characteristics are different. So in that case, since the groups are different, so we'll perform independent t-test. From here, I will take one data. This data can be used for Anova also, t-test also. So open, and from data library, this tooth growth. So this is the length of the tooth. This is the metric variable. So I already told you that for independent t-test, your outcome variable or dependent variable should be metric in nature. If it is non-metric, then you have to perform the non-parametric equivalent, that is Mann-Whitney test. But if it is metric, then you can perform independent t-test, provided that your this data, that is dependent variable, which is the tooth length in this case, should be metric, and your independent variable is categorical and should be divided into only two categories coming from different population. So what is this? This is the type of supplement: vitamin C and orange juice. So supplements are given to the people in the form of, to one group it was given in the form of vitamin C, to the other group it was given vitamin C tablets, and to the other group it was given in the form of orange juice. And then their tooth length was measured. And we are interested in knowing that whether vitamin C and orange juice have the same effect on the tooth growth, or there is a significant difference. Are you getting this problem?
Yes, sir.
So vitamin C tablet is a different kind of thing, orange juice is a different kind of thing. It is our one independent variable, that is type of supplement, divided into two categories and length. This is metric. So since it is metric, further we will test its normality also, and also we will test, since we are doing independent t-test, we will also test homogeneity of variance. So first let's do independent t-test. So go to analyze t-test, independent t-test, and select tooth length independent variable, and grouping variable or categorical variable will be. Since I am not taking those because it is having three categories, it will make it a case of ANOVA. It should have only two categories. This is the grouping variable. So P is less than 0.05 or greater than 0.05. Here if you see P is greater than 0.05, that means there exists no significant difference between both the supplements. Means orange juice or vitamin C. Supplement given in any of the form will have the same effect on tooth growth. There won't be any difference. Let's test the homogeneity test. There is a homogeneity of variance. P is greater than 0.5, 0.05. The normality test. Again, here P is greater than 0.05. So the data is following all assumptions of independent t-test. As I have shown yesterday in the decision tree, I will show you again. It is. No, from there, made a decision tree, which I have shown you yesterday. Earlier, sorry. So this is our decision tree. That if you have one independent variable coming from two different populations which are mutually exclusive of each other, then test whether the dependent variable is metric or continuous. If it is metric, if it is categorical, then directly move on to the non-parametric equivalent. In our case, it's length, which is a metric data, okay, the tooth length. Then further we checked for normality through Shapiro test, that also found to be normally distributed. Levin's test of homogeneity of variances also found to be true. So finally, the independent t-test that we applied is true. Now, from this we can infer that since p is greater than 0.05, so null hypothesis cannot be rejected, and null hypothesis says that there is no significant difference between orange juice and vitamin C on tooth length, means they are having the same effect. Now let's see results can be generalized in the population or not. So here you can see that Cohen's d is 0.49495. So again, okay, sorry. So if you see, if you convert it into percentages, it's 49.5% it is coming to be. So it can explain to the level of 49.5%. So to some extent, this can be generalized in the population. Means the sample that you are getting, the result you are getting from the sample, that will have an effect to a level of 49.5%. So if it is 100% and fully generalizable, else 49.5% it can, the result that you got from your sample in the entire population, if you give the orange juice and vitamin C as supplement to different groups, it will show, it will have no effect, but only this effect is limited to a level of 49.5%. So if you are taking a population of 100, so this effect will be visible, that there is no significant difference, will be visible only in 49.5%. Is this clear?
Yes, sir.
Fine. Now let's do ANOVA also. ANOVA is nothing but the extension of independent t-test. All things remain the same. Only thing that changes that your categorical variable is more than 2. It could be 3, 4, till 2 it is independent t-test. More than 2, it is a case of ANOVA. Now you might be questioning that we can apply 2 times independent test and get the result. Let's say we have 3 groups. Group 1, group 2, group 3. So once we can compare group 1 with group 2, one independent t-test. Then we can compare group 2 with group 3. And then we can compare group 1 with group 3. Right? Like this also we can do. This is the independent t-test. Comparing two groups at a time, 3 times we can do. But why we are doing ANOVA? The answer lies in a simple question thing that in statistics, every outcome equal to model plus error, right? Is every and this model is nothing but the statistical model, that is the t-test or ANOVA or correlation regression, whatever you are doing. Now, if I am doing this 3 times, so first time I am getting this is the outcome one will be model one plus error one. This outcome will be equal to model two plus error two, because none of the statistical model can be 100% accurate. So there will be error, residual errors. Model 3 plus error 3. If you do by this, and if you compare all at once, group 1 versus group 2 versus group 3 through ANOVA, we will get model plus error. Which one is better? This approach or this approach?
So the ANOVA one.
The ANOVA. So we have to try to minimize this error actually. That's why we, rather than if you have more than two categories, rather than doing it, it can be the results can be obtained through doing independent test between two groups separately. But ultimately, you will end up in getting more errors, and we always try to minimize the errors. So here you will get only one error only once. That's why, because every outcome, please keep in mind, every outcome is equal to model plus error. If you know regression, that's how we write y is equal to b0 plus bx. This equation is not complete until we write e, and this one is nothing but your statistical model. So every statistical treatment is prone to errors because there will be some data points that will lie as residuals. So we need to try, we always try to minimize this error. So always go with a statistical model which can minimize your error. So we already have ANOVA which can do comparisons side by side among many number of groups. If you have 10 groups, then also you can do the ANOVA rather than doing it 10 times separately. So here, rather than taking this, we will take the dose. Now this dose, if you see the data, is divided into three categories: 500 mg, 1000 mg, and 2000 mg. Now we will see the effect of the dose on growth of the tooth or length of the tooth. Now it is the three groups, so we will conduct ANOVA here. We won't conduct independent t-test. So ANOVA is nothing but an extension of independent t-test. So we will take tooth length, we will take dose, and here also p is less than 0.05. So we will say that there exists a significant difference between different dose levels on tooth length. So this ANOVA will only tell you that whether there exists a significant difference between the three doses on tooth length or not. But which of them is different, which of them is showing a different effect, that you cannot know. That you will come to know through post hoc test, which is multiple comparison. So for one way ANOVA, we use the Tucky test. Now here you can see. Now p value of 5000. with 5,000 when compared to 1,000, it is different. When compared to 2,000, it is different. Means then you compare this 1,000 mg, 1,000 mg is not showing significant difference with anyone. 2,000 mg is showing significant difference with all. Here 1,000 mg is showing with 1,000 it won't show, and here is 1,000 mg is showing a difference with 2,000 mg. But so if you see 500 compared to 1,000 and 2,000 mg, there exists a significant difference. 1,000 mg when compared to 2,000 mg only, then it is showing a difference, and 2,000 mg is showing a difference with all. So you can say that all the three doses have a different effect on tooth length because all are differing from each other. Means all are showing a different effect. So all are having a all are having a different effect on the tooth length. Now, if you want to see this, whether it follows the assumptions, so yes, homogeneity of variance is followed, normality test, that also is followed. So it is following the assumptions also, and you can say that first through ANOVA, you can say that there exists a significant difference of the dose on the tooth length or the growth of the tooth. And when you have done multiple comparison to further explore it, you found that all the all these doses were significantly different from each other, means all were having different effect on the tooth length. 500 mg was having different effect, 1,000 mg was having different effect, and 2,000 mg was again having different effect. And all these were significant, all these differences were significant. If you want to test significant, you can select this flag significant comparisons. So it will tell you which one is significant. All these are significant. So it will tell you that all these are values are significant. So all are having significant difference. So this is about one-way ANOVA. Is this clear?
Yes, sir.
Or do I need to repeat it?
So can you show from where you tested the significance thing? I couldn't see it. I was simultaneously
This
opening my
this
Zoom.
this one flag significant comparisons.
Okay, sir. Okay.
If you click this post hoc test, you will get the option for post hoc. Okay, and here you can select flag significant comparisons.
Okay, sir. Thank
Okay.
you.
Now another one is paired sample t-test. Paired sample t-test is used when you have two groups, but that two groups is not coming from different population, from the same population. Means from the same people. Let's say a pre and a post situation. Same person in two different situations. Let's say you have taught mathematics in the class and statistics in the class, and you want to test whether there is a significant difference between the scores of mathematics and statistics of the same student. Here you are having two different situations, two different groups, but they are from the same population. They are not different. They are not coming from the different population. Or you want to test the effect of paracetamol tablet before fever and effect of paracetamol tablet on fever before it was given and after it was given. What was the fever? Whether there is a significant effect of it or not. Or you want to test the reduction in weight or weight loss of a person undergoing a gym training after first month, after third month, after 6 months, something like that. So same person will be there. Then this will make it a case of pair t-test. So for that again I will use this data. open this data, bugs. Already I have explained you this data that in this data what we are trying to measure, we are trying to measure people's intention to kill a bug based on the frightenness of the bug and disgustingness of the bug. Means how much frightening that bug or that insect is and how much disgusting it is. So based on that, so let's take the two cases, LDLF and LDHF. Means low disgusting and low frightening. Here the bug is low disgusting but high frightening. In these two different situations, people have different intentions. Whether these different intentions taken on a scale of 10 is significantly different or not. So people remains the same. So if this is the case, then we will. Are you getting the problem situation?
Yes, sir.
So here two different groups are formed, but based on two different situations, people are the same. So your two groups are not coming from different populations, from the same population. If you see this, means you have dependent samples. If it is a categorical data, then directly move on to the non-parametric equivalent, that is Wilcoxon test. If it's a metric data, then check its normality if it is followed. Since it is coming from the same population, you need not to check the homogeneity of variance. So only normal distribution and move on to the Prt test. So here if you see, this is taken on a scale of 10 and they score their intention to kill that insect based on the insect's this disgustingness and frightening uh, attribute. So low disgusting and low frightening insect and low disgusting and high frightening insect. What is the intention of the people? This is the metric measurement. Let's see through independent t-test on the same population, same people. So paired sample t-test, take this LDLF and LDHF. One pair you have found. See, yes, there exists a significant difference. Means people intention to kill a low disgusting and low frightening insect and low disgusting and high frightening insect is different. The scores are different. And let's check for assumptions, normality, because here homogeneity we cannot check. So normally this data is not normally distributed, so it makes it a better fit for Wilcoxon test. Or we can change one more way. So actually this is not normally distributed, so this assumption is not fulfilled. How we do a test, that you can come to know, but ideally it is not true you for doing a pair t-test because the data is not normally distributed. So you can perform a non-parametric equivalent of it. So this is how we do the t-test, but in assumptions we found that it is not correct. So we will do the this one paired samples. Or t-test. There should be non-parametric. Anova we are getting test. Let's say pair t-test we are taking, but here it is not giving the option of Wilcoxon test. I'll check and come back to you. Or if we need to code, then we will code it for doing. There should be some option if it is not following. Yes, here in the pair t-test only it is giving Wilcoxon rank test. So since data was not normally distributed, if you have seen here, so we cannot perform pair t-test. So we will perform its non-parametric equivalent, that is Wilcoxon rank test. and select these two variables. And now we can say that there exists a significant difference among the intention of the people. And this we have done through Wilcoxon test rather than Prt test, right? So here we will report this Wilcoxon value, not this one, because data is not normally distributed. Is it clear?
Yes, sir.
And if you want to check the effect size, you can again click the effect size at 95% confidence interval, coherence D. It is coming to be negatively 69.7%, so leave it, means it is not having appropriate effect on the entire population. So if the data has been normally distributed, then we could have reported this, that there exists no significant difference based on Prt test. But since data is not normally distributed, so we will select here only Wilcoxon one test, the non-parametric equivalent, and we will report only this. That since P is less than 0.05, this means that there exists a significant difference between the people intention to kill the insects based on their this frightiness and disgustness level. Right? Is that clear?
Yes, sir.
Okay. So ANOVA and T test we have covered, and tomorrow again, though it's not mentioned, but it is one way ANOVA. Tomorrow I will be covering two way ANOVA.